Welcome to lecture number 3. In this lesson, the learning objectives are to understand mole and balanced chemical equations relationship. A true essence of why we study balanced chemical equation or stoichiometry and the moles. What is the relationship of moles in the balanced chemical equation, and what information does it gives us, and how this becomes handy in devising a chemical reactions at industrial level. So let's find out that what balanced chemical equation tells us about. So when we look at the balanced chemical equation, this basically talks about the ratios of atoms in the molecules of reactant that is exactly balance the ratio of atoms in the molecules of products. In the first lesson, we did talk about one of the Haber's process reaction, which is nitrogen reacting with hydrogen, and it is producing ammonia. So ratios of atoms in the molecules of reactant, we will be looking at that. So here we have 2 atoms of nitrogen. Here we have 2 atoms of hydrogen. And what is the ratio of atoms in the molecules of products? So here we have 1 atom of nitrogen and we have 3 atoms of hydrogen. So we see that they are not balanced. So when we balance the chemical equation, we basically balance these ratios of atoms both on the reactant side as well as on the product side. So what we do, we make the odd one into the even form. So why not to multiply this by 2? So times 2 and times 2. What do we get? Now we get 2 atoms of nitrogen and we get 6 atoms of hydrogen. So this one here and this one here becomes balanced, but this one here and this one, they are not balanced till now. So what we need to do, we are going to multiply it by a factor 3, and we are going to place 3 here as well, because this is the number coming from the equation. So this becomes now 6 hydrogens. So my equation will take a shape of that nitrogen reacts with 3 parts of hydrogen, which forms 2 parts of ammonia. So these are the coefficients, these are the coefficients that we place next to the hydrogen or ammonia, and they makes the moles. And when there is nothing written here, they are considered as 1. So here it says that 1 mole of nitrogen actually reacts with 3 moles of hydrogen, and it will produce 2 moles of ammonia. So they gives us a ratio that they are going to react in a 1:3 parts, telling us that I have to take some amount of nitrogen which is in 1 part to the 3 parts of hydrogen. So we will be taking them, like say for example, I have taken 20 grams of nitrogen or 20 moles of nitrogen. I will be taking 60 moles of hydrogen, which is 1:3 ratio. So this gives us a sense, or this gives us a clear notion that we have to take the amounts of substances in a particular quantity which is coming from the balanced chemical equation, which becomes a scale. So this scale basically tells us that what amount in ratios of the reactants that we are going to use to produce a product. So it will help us in preventing the wastage, or it will help us in overcoming the cost, the time that will be consumed during this whole process. So we control these factors, and that is how the industries are set. And they basically used a good concept of moles and balanced chemical equations. So let's dig deep into this relationship. Let's say we have 64 moles of sulfur dioxide which is burnt in excess of oxygen. So what number of moles of sulfur trioxide is produced? So first we need to look into that what actually the reaction is. The reaction is between this sulfur dioxide and oxygen, and the product which is produced is sulfur trioxide. So let's place them in order. So sulfur dioxide reacting with oxygen, it will produce sulfur trioxide. And we see that the equation is not balanced. We need to balance it. Using the above method or rules, you can balance it, and you will get that there are 2 moles of sulfur trioxide which are being produced, and 2 moles of sulfur dioxide is needed to react with oxygen to produce those 2 moles of sulfur trioxide. So now this becomes a scale, and our scale is actually a balanced chemical equation. So now using the balanced chemical equation, we will be finding out that what amount is going to be produced when we burn 64 moles of sulfur dioxide. So this scale tells me that it is a ratio between a sulfur dioxide and sulfur trioxide, because it tells us that we have taken 64 moles of sulfur dioxide and it has produced 60, it will going to produce how many moles of sulfur trioxide. So we need to find out that. So the relationship is between sulfur dioxide and sulfur trioxide. The scale tells me that when 2 moles reacts, it will produce 2 moles. So if I take 64 moles, this is going to produce X, which is equals to 64 cross 2 upon 2, we get 64 moles again. Moles of sulfur trioxide. Now, this problem is a very direct problem in which you see that the scale is in a 1:1 relationship. This means that whatever the starting material, the amount of starting material that I take, it's gonna give me the very same amount. So this is a direct problem. Let's look into another problem. In a Haber process, 16 moles of hydrogen is allowed to react with nitrogen. So what number of moles of ammonia will be produced? So from the problem, I'm going to inspect that what are reacting and what is the product that is being produced. So hydrogen and nitrogen are allowed to react, and ammonia is what is going to be produced. So our equation becomes like nitrogen reacting with hydrogen, and it will produce ammonia. Equation is not balanced, but you have seen the method above, so this will be like 2 here and 3 here. So the scale tells me that 3 mole is reacting and it is producing 2 moles. There is a ratio which is not 1:1 relationship, right? And since they haven't even discussed about nitrogen in a way that what amount of nitrogen was taken, they just said that it is reacted with nitrogen. So we just leave that for a time being. So what number of moles of ammonia will be produced? So we have 3 moles reacting with 2 moles, 3 moles producing 2 moles. So this scale tells me that if I have hydrogen ratios ammonia, then 3 mole is producing 2 moles. So 16 moles will be producing how much? That is X. So X is equals to 16 cross of 2 divided by 3. What do we get? we get 10.66 moles of ammonia. Now you see, the above problem is a very direct problem, but the second problem, example problem, that is not a direct relationship. This is a relationship that requires to do some math, or you can see that this is working in a ratio. So we see that what we need to have is a better understanding of the balanced chemical equation. We should have a balanced chemical equation so we can find out the amount of substances that we are going to need. So you can also make it sure that this balanced chemical equation becomes a recipe, that how much of each substance as in reactants are needed to react together to produce a product of our choice, or to produce a product of the amount that we need. So we can work in either ways. Let's look into the mole mass relationship and balanced chemical equation. Now we are getting into a deeper stuff. That was a bit surface stuff mean like very direct approach, a very simple approach. But in real life, we are not dealing in a direct approaches. There are many hidden things that we need to look into. So these hidden things requires a good maths, and there becomes many different relationships that need to be worked out in the same time or in a real time. So mole mass relationship, mole and mass relationship and balanced chemical equation. So in this problem, we are provided with 40 grams of calcium carbonate, which is decomposed thermally, and it is asking about that what amount in moles of carbon dioxide will be produced. So whenever you read a question, you should underline the important points, the points which are the data and the points which are asking for the stuff that you need to do the maths for. So 40 grams of calcium carbonate and what amount in number of moles of carbon dioxide will be produced. But how will I proceed? Until or unless I have a balanced chemical equation, I can't proceed. So first I need to find out that what is the balanced chemical equation. So this is the starting material which is thermally decomposed. So we have calcium carbonate. This one thermally decomposed, it will produce calcium oxide along with carbon dioxide. And if you see that the number of atoms here, we have one atom of calcium, we have one atom of carbon, and we have 3 atoms of oxygen here. Here we have 1 atom of calcium, we have 1 atom of carbon, and 2 and 1 we have again 3 atoms of oxygen. So this equation is balanced all the way. So this tells us that 1 mole, if decomposed, this is going to produce 1 mole of calcium oxide and 1 mole of carbon dioxide. So our relationship is set, our scale is set, that it is a very simple ratio in which 1 mole is producing 1 mole of anything or 1 mole of products. So, but since the equation works in moles or can be read in moles, but we are provided with 40 grams. So we need to convert this 40 grams into number of moles first. So our step 1 is the conversion of mass to number of moles. So for this we must have the MR. So what is the MR of calcium carbonate? So this is 1 cross of 40 plus, this 40 is the atomic mass of calcium. 1 cross of 12, this is the atomic mass of carbon, plus 3 cross of 16, this is the atomic mass of oxygen. We get 100 grams per mole. So for number of moles, this is equals to mass over the MR. So we have mass, that is 40 divided by 100, we get 0.4 moles. So now we are going to do a step 2 in which we will be finding out the relationship using the balanced chemical equation as a scale to find out that what amount in number of moles of carbon dioxide will be produced. So we have calcium carbonate ratio carbon dioxide, so 1:1. This is a scale coming from the balanced chemical equation. So 0.4 moles will produce how much? That is X. So X is equals to 0.4 moles because this is a direct relationship. So we are done with finding out the number of moles of carbon dioxide that are produced in this process. But the real question and the real problem that student faces is that they do not need to find it necessary to convert the mass into moles, and they say that since this is a direct relationship, so 40 grams of calcium carbonate will be producing the very same 40 grams of carbon dioxide. But I say that is a wrong approach. Let's find out that how this is a wrong approach using mass to do the maths of balanced chemical equation. So the wrong approach that student uses, they say that we are provided with calcium carbonate, it is producing carbon dioxide, they have 1:1 ratio. So this means that if we have taken 40 grams of calcium carbonate, it will definitely produce 40 grams of carbon dioxide because this is a 1:1 relationship. But I say this is very wrong. Why it is very wrong? Let's find out. The above calculation that we did, it gives us 0.4 moles of carbon dioxide. So let's convert these number of moles into the mass of carbon dioxide that is actually produced. So mR of carbon dioxide, this is equals to 1 cross of 12 plus 2 cross of 16. What do we get? We get 44 grams per mole. So mass will be equivalent to number of moles times the mR. So number of moles is 0.4 that we have calculated here times 44. We end up with the value which is, let's work it out on the calculator. 0.4 cross 44, this comes out to be 17.6 grams. So you see the equation, the balanced chemical equation, and the mole concept, mole and mass interconversion concept that we used, it gives us that it produces 17.6 grams of carbon dioxide, not the 40 grams. So we never do our calculations in mass. Even if they have given you the mass of substances, you first need to convert it into number of moles, because whatever the mass is there in a reactant, and let's say in this calcium carbonate, it is decomposed. Now the mass is distributed among the two different types of molecules like calcium oxide and carbon dioxide. So it should not be the very same amount that is going to be produced. So that is why we don't do our calculations in mass. We do our calculation in moles. So mark my words, you'll be using moles to find out or to work out or do all the maths to work out the problem. You are not going to do your calculation in mass, since we found out that why it is necessary to work out our problems in moles. So good luck with that.